Hello everyone, today I'm going to deliver a lecture on which is Spectra design. The design course is contain the various topic which is response spectrum and equivalent static force, and then response spectrum analysis, equivalent static force analysis or method, uh, earthquake response spectra for BNBC 2020. The BNBC 2020 is for Bangladesh National Building Code, and elastic dynamics versus equivalent static analysis, elastic dynamic analysis and equivalent static force method, and some math examples. So let's start. So here is a response spectrum. We can see here, if we multiply with 1 times, as we know, f equal k u equal to f. This is the elastic, what I will say, this is the elastic, this is the static formula. And now we will go to the response spectrum. We know f equal to ma, and then we will use f equal to ma and k equal to remain state. And we are using the where we have used the damping, that's why, and we will use the mass. So damping, if we use the integration of the displacement 1 time, then we will get the damping. And if we integration is 2 times, if we differentiation in 2 times of ultimate, that will be the mass. So it will be not integration, sorry, it will be differentiation. So and in this way we have at first we know the what is the response spectrum. Okay, so as we have been seen here, the response spectrum is a graphical summarization of the maximum response of single degree of freedom in a ground motion. It is the solved of equation of motion for a single degree of freedom at each period of the interest. One varies first, second, and third, and fifth stories or building is subjected to earthquakes or as a single degree of freedom, then some of the acceleration, displacement, and velocity graph has been being calculated, and it is called the response spectrum. So we can see the different of building, as we have been seeing 10 story, 20 story, 50 story, and 100 story building. So if the ground motion or acceleration or if the ground motion is applied on the building, we can say El Centro, Kobe, Northeast, then we have been seeing the this 10-story building will be 1 second, and 20 stories building will be 2 second, and 50 stories building 5 second, and 100 stories building 1 second. So if we calculate all the sum in displacement 1, 2, 3, 4, so all the, then we'll found the time versus displacement. As we displacement of in the first building, this building found the displacement is let's say is 5, and then it is taken for it is taken for 2, and then this is the 25, and this is 5. In this way, the larger building will get the larger displacement. While the acceleration we will compare, then we will found this type of acceleration, and if we compare, the velocity will be this type of. And if we seen the velocity, acceleration, and displacement, all the 3 types of graph are given here. So we can see the figure in that the summation of displacement line is being increased, and summation of velocity is also being increased. So displacement and this is the velocity, and this is the increase with the respect to the time of the period of the graph. So if we go to the here, some this taken from the Professor Dr. Iftikhar Anam sir, University of Asia Pacific, the professor. So the response spectrum, the time domain response time history is procedure the prescribed numerical single degree of system provide the structural response with time, but the design structural member usually based on the peak response, and the maximum value of the design forces. Therefore, the main subject of the seismic design method is to be conventionally calculated, and peak displacement and forces result on the particularly design ground motion. The response spectrum analysis is a approximate method of the dynamic analysis that can be readily used for the reasonably accurate prediction dynamic response ground motion. So we have been seen already in my here. So if we can see the static load F equal to K, and if we integrate the displacement one time, then we will feel the um, uh, then we will get the damping. If we differentiation in two times, then we will get the mass. So now we will dividing all the m, then this like this physical will be appeared. So root over k by m, so root over k equal to m. We know the k divided by m equal to root over k omega square, which is rational natural frequencies. This is the taken from here. And the other one we can see c by m. So if we know the c equal root over psi equal root over km, it is taken from the single degree of freedom, and now we'll divided 2 in both sides is m, and found 2 psi equal to root over m, and calculating in this area and found root over 2 phi into root over 2 psi into omega. Okay. So so root over c divided by m equal to 2 psi equal to 2 psi equal to omega. It is taken from this derivation and described by it. So this is basically this is the response spectrum equation we have been using as per from taken the SARS note, and this is the response. Shown in previous lecture, the governing single degree of freedom in ground motion, we know this is the single degree of ground motion, and since the load is themselves on right of the equation, the proportion of the structural properties, each of this equation is nominalized in terms of properties and natural frequency and damping ratio of the ground motion and acceleration displacement velocity. For example, is here. For a specified ground motion, El Centro, Kobe or others in temporary variation structural displacement velocity acceleration depends on the natural frequency and the damping ratio. From the series of the obtained maximum parameter of identify easily to maximum design criteria for particle structure and that particular ground motion. Such maximum value similarly obtained for the structure with different natural frequency of period damping ratio. And since the natural period Tn is more familiar than omega, and the peak response of represented the function Tn and psi for the ground motion acceleration. So standard ground motion data is chosen for design of single degree of freedom. The maximum response of the will be depend on the two structural properties. A plot of two below response of quantities of function of Tn and psi is called the response spectrum. So we can see that Tn damping ratio is response spectrum, that a particular quantity such as group is obtained from the familiar damping ratio and the provided plot of the seismic analysis single degree of system. So we can see the another following the peak ground acceleration displacement and velocity acceleration is called response spectra for relative deformation velocity and acceleration. So these are the equation. Such the representation having the long useful tools, so we can see here the lots of information is given. However, the response spectrum method from the some serious shortage than the compared to the numerical domain analysis. Although one can be obtained from response spectrum for any given ground motion data, spectra used in building codes while buried in El Centro data. Thus, they may not represent the more severe earthquake that have since correct. So beside that method needs model analysis and obtain structural natural frequencies which can be laborious tasks. Okay, so moreover the method cannot be applied non-linear structure, or it can be predict structural failure. So it is necessary a linear analysis, but it approximately used for non-linear structure applying ductility factor to reduce the amplitude. So we can see here the graph is given here, the previous graph 1 to 3. So if you know the natural frequency and psi, then we can find out acceleration, velocity and displacement. So this is our assumption for response spectrum. So as at first we have been seeing here the when the damping ratio 0, mass and stiffness are given, then acceleration will be 2 2. Okay. Then acceleration will be to 2 2. Then omega equal to root over km equal to, we have been found natural frequency and time period 2 pi into omega and found 1.26. Here is the 1.26. And another method when we'll change the mass, damping coefficient and stiffness, then we can found the natural frequency 2.51 and 2.51. And when we see the we change the parameter stiffness, mass and c, then we have been found a natural time period 0.60. The different value we have been found in different stiffness and mass. And the acceleration we have been found 0.22, which is we are seeing here the 0.22. And the another acceleration we have been found 5, which is the 5. And another acceleration we have been found 1.15, so 15. So we can see the different acceleration we have been found from different time periods. So these are the summation of all the summation of the different acceleration and different time period as a one building. So we can summarize all things in the response spectrum. So we can see velocity of response spectrum, it is increase and then decrease only. And displacement response spectrum, we can see the increase the displacement with the time period. So we can see another response, which is structural response C equal to mx. We have been found from building structure by ASC constant average method. And maximum ground motion we have been found from El Centro or other Kobe northeast, and in this way we have been found 2.2. And another we have been found 5.0 and another found 1.5. So 2.2, 1.5 and another 0.5. These are the summation of the response spectrum. So structural response is given in this figure. So time period is x-axis and y-axis is c. This is called structural response C. So we have been seeing the equivalent static force. Now we can see here the acceleration spectrum in different sites. We can have different soil parameter: hard soil, medium soil, and soft soil. And the code specified acceleration spectrum we can see in hard soil, medium soil, and soft soil. These are the spectrum for divided by g, which is acceleration versus g equal to gravity. So now we'll see the what is the static analysis. Okay, so equivalent static analysis, we know F equal to ma. This is the very easiest we know from physics and somewhere else. So F equal to ma, m equal to, we know the W into g, and we know A equal to A divided, we are using AG into AG as we will be cancelled out. And then if we use we can take in here W, and AG equal to G is taken from here, and AG by GB is remains same. So AG by G is nothing but this is Z. I will get if the if we get the an earthquake that is given this type of phenomena, then if we found 8 feet per second square, that is the A. So if we divided by acceleration, which is 32.2 or 9.8 for SY, and found 0.25, this is the called J, and it is come from AG by G. And A divided by G is nothing but it is the structural response or damping. We have been not damping, this is the structural response. We have been shown in previously. I will get the structural response. And W is nothing but when we know that W is a seismic weight or mass of the building. So we know base shear equal to ZIC by W into G. As the structural importance, it is taken from different zones. It is very. Now, so you can show displacement and force graph is given here. Uh, so if we go the equivalent static method, so equivalent static analysis is a seismic based on the concept of the replacement inner force of the various lumps masses. Okay. By the equivalent horizontal forces and properties of the weight of the body, therefore mass is displacement, therefore acceleration. Okay, summation of this concentrated force is balanced by the base shear and base shear structure. This method may be used for structural seismic response for all structural specified in building code. The following provisions are taken uniform building code of USA also valid from for Bangladesh National Building Code. It is the oldest code, as we know, the base shear ZIC by W. So we will not use these, and T equal to given this formula. Okay, so we can see the structural period is given here. The vertical force is also given here. Others building code is compared in SAR, and the structural dynamics building code is given here. So earthquake response spectra upcoming. This is not upcoming. It will be 2020, as it is already published in government of Bangladesh. So we can see the base share of 2020 is 2/3 ZIC by W, and Z value is varying 0.12, 0.20, 0.210, 0.36. Select my machine and choreograph. So we can see that there is a zone 1, and zone 2 is here, and zone 3 and zone 4. So these are the different zone. And see, we know it is depend on the time period. And TC, TB, TC, it is also depends on the soil classification. SB, SC, ST is a soil type. And damping coefficient, we can use eta equal to root over 10 into 5 into 5. When psi equal to 0.5%, then we can use eta equal to 1. So we can use the time period 0.04 for RC structure, and 0.0724 H to the power 08 for steel structure. So in this way we can calculate the F, which is B equal to summation of HI WIHI, and K is found from condition of T. And linear interpolation we can use, then we can found this type of a spectra, and BNBC response spectra for SA, SD, and SC with respect to the different soil parameter. So if we go to the and this is the proposed it is not proposed, it is published BNBC 2020 spectra. On the other hand, we have been seeing the El Centro, which is the dotted in this line, and the Kobe is this is the Kobe earthquake, and another is proposed BNBC. It is 93. It is already invalid, and new BNBC also have been seen. This is proposed. So this is the spectra. So if we seen here, the another which is base shear is taken M1, M2, M3. So so base shear will be divided in different masses. So mass will be story 1, story 2, story 3, and it will be found the different 3 deflected shape also. Deflected is a mass deflected found in the top story, and we can see here the mode shape also. So soil factor we have been see the C, which is given a maximum from structure, and divided by a from earthquake, and it will comes from the value of C, which is structural response. Okay. So note that if we fill the soil, then the filled soil is very hazard and very dangerous for earthquake. And now we can see response spectrum from BNBC 2020 we've been seeing B equal to 230 into Z twice into W and found here. So in the previously we have been found if we multiply into 2/3, then we will go to the previous uh, um, uh, uh, earthquake. So we will not take the previous value, but we will take 0.12, 0.20, 0.28, 0.36. Okay, so you can see here the and if for the tall building there is no problem for earthquake, but on the other hand there is a problem in wind for the tall building. As have been seen for tall building, the C value, structural response C value is much lower value. Here we can see the 4 zone is divided in Bangladesh: Zone 1.12, Zone 2.20, Zone 3.28, Zone 4 is 0.40. So you can see the here I am also writing base here, and Z value is different, and C value is depends on the different different T value. I am also taken another lecture how will get the how will define how I will draw the response spectrum. So please watch my video also. And dumping correction is given is eta equal to 10 into phi. Psi the value of dumping psi is always 5% for RC structure, and found psi equal to 1. And time period we have been used different RC value, and we can use T equal to year or we can use the another thumb rule, which is the number of stories divided by 10, and then we will get the easily time period. It is taken from our sir, Dr. Tekaranam sir, the thumb rule. And another we can use the T value in the different parameter, but we will using this as could provide me for our from our judgment. Then we can keep in mind that we can use the different time period by using that formula. So you can see here the soil type SBS, CSD, and SC, and we can see the time period 0.122. So we can use here. So let's see an example when T equal to 0.5 for hard strata, C equal to what, then N equal to 1, and dumping ratio of 5, and putting all these value and found C equal to 0.96. So the value will be C equal to 0.96. Okay, if we get the 0.51 the time period, then what will be our C value when we have been found 3.6, and if we calculate it here and 3.6 another value time period we have been found 0.51. So we now will checking the what is the value of time period. It is between B or C, or C or D, and in this way calculating here, and we will find the also forces also. Okay, so now we'll see the another elastic dynamic analysis versus equivalent. So I have already explained here the response spectrum analysis, and now I have been shown the equivalent static analysis or method. So two type are completed, and then we have been seeing the earthquake response spectrum analysis of 2020. I am explained here. Now I am going to the elastic dynamic analysis versus equivalent static analysis, or equivalent static analysis and equivalent static force method. So let's see. Before I'm going to this, then I want to see here the having the point of my analogy between response spectrum analysis and equivalent static method. It is this sector compares some numerical results between two methods. Of central importance of the term base shear, the use E ESFM, which is equivalent static force method. Okay, which is the static force at the base of the ground floor column developed due to the ground motion. So we can see here the when the damping ratio is 5, then the spectrum is like this. For response spectrum, L centro 5% ground damping ratio and 2% and damping ratio will be like that. And response spectrum for 5% ground motion, we can see the L center is giving like that, and Kobe is the this line Kobe, and the north is another ground motion we've been seeing here, north is, and BNBC proposed is as previous BNBC is like that. So shown the various figure 2 this shown the various of C and L center out, which is GABA damping ratio 5 and 2%, this graph, while the figure this figure it shows the various C. This is the C value is different C value for L center, Kobe, and Northridge, and Northridge are data for damping ratio 5% as well as the design value suggested by BNBC. Okay, so let's see another example we have been seen here. For the single degree, now we'll going this topic also covered. Now I'm going to explain the some math example. So this is the math example of elastic analysis and equivalent static forces. Okay, so let's see the single degree of system desire. Describe M is given, K is given, C is given. Calculate the base shear. So we have to calculate base shear. Why? Because we have been seen here given the base shear is a equivalent static force method. So that's why we are calculating the base shear. So for sake of the equivalent static method, now we are calculating the base shear. So we have to calculate L centro, Kobe, BNBC 93 and BNBC 2020. It will be 2020. So let's see, we using Z for L centro, Kobe and Dhaka. Okay. So we have been found M value and K value and C value. Now we are calculating omega equal root over Km and found, and T value is found, and damping phi equal to given. For L centro ground motion, we have been taken 10.07. This ground motion are taken from L centro. If we go to the L centro ground motion, then we have been found here the L centro ground motion as equal to 10.07. So I'm opening my this is the L centro ground motion, which is the right color. If I will off this here, then we can see the L centro bar. The maximum value have been found almost 10, or if it is taken here the 10.07. So these are taken 10.07 from L centro ground motion, and divided by G, we have been found 2.07 and found 3.13. And the 0.93 is taken from L centro response spectrum graph, or T versus C graph. If we take the C versus C graph, then we will found the 9.3. And W equal to, if been found 1 into 3, and the base shear equal to ZIC into W. So and C value will be changed, and the Z value will be changed, and W is remain same, and found 9.4. And the relative displacement equal to use K equal to P equal to K, and found relative displacement 0.37. Or if we use C into AG max from Lg into W square for a quick calculation or our calculation purposes, then we can found 37. So if you use this on-off method from to this, it will be depend on you which method will you follow, but two methods are same. And now we'll go to the another earthquake, which is Kobe. We'll taking the mx. How we'll get from this ground motion taken from peer ground motion or NHL. and found this, or it will be given in question if you know. But in practical field you have to download this ground motion and found 7.79 and divided by 32.17 is value of G, and found 0.55. When you found the Kobe, ground motion Kobe, and time period is found 1.275, and with respect to 1.275, then you will find 1.57. Why you will take in 1.257? Because the based on the based on this information we have been found 1.275. That's why we will go to the 1.275 in Alcento graph and found C value. In this way we are calculating the value of C, and the same way we are calculating when we take in the graph of Kobe ground motion, then we will taking this graph which is C value, and found C value 1.57. And in this way W equal to 1.1 into 32.5, and base shear will be calculate B equal to Z CW, and found 27. Now we'll calculate the relative displacement P equal to KU and putting all value, and found 1.17, or we use C equal to AG max. AG is found, how will case AG max? We have taken the LCM to, that's why in this way we will found AG from the graph. The maximum AG to 17.79, and C value is found the time period respect to the from graph of Kobe. And omega we know, omega already we have been founding here 5 radian per second, and putting on information and found 1.1. So as the previous BNBC we have been seen here, C equal to 2.5, and using this formula and found 1.07, and which is less than 2.57. So if we summarize here the three value, which is El Centro, Kobe, and Dhaka zone. So base shear we we have been found 10 for Kobe. If you use the El Centro ground motion is 10.8, and if we use the Kobe ground motion, seismic ground motion, then we will be found 19.1. And if we use the base shear of the Dhaka, then we will found 5.1. So corresponding the maximum relative displacement also 0.43, 0.76, and 0.27 respectively. Now we can see from new BNBC we'll use this 0.17. 0.17 have been found from ETFs, and we can see here the or the calculation. Then we have been seeing the TC value 0.4 and T and equal to 0.20, and found the S value, C value, putting all these value, and found the C value 0.796. And W equal to M equal to G we have been found here, and L Centro data is given from the L Centro data we have been found the 8.01 the base shear, and the Kobe will be 14.16, and the Dhaka zone will be 30.41. So maximum relative displacement 0.56, 0.21, and 1.13 respectively. So that was our that was covered the elastic dynamic analysis versus equivalent static force method we've been seeing here. We are taking the equivalent static method we have been found in Dhaka 3.41. On the other hand, elastic we have been seen the elastic dynamic analysis we have been found 8.01, which is greater than the equivalent static method. In the same way, we have been also found here the these data are elastic dynamic analysis, which is found 10 and 19, and we have been found equivalent static method. So we can see the elastic dynamic analysis found the base shear is much greater than equivalent static method. But we have been found the different displacement also. When the displacement also is greater in equivalent elastic dynamic analysis, and less value is we have found in the equivalent static analysis. Okay, so let's see some example. It will be for let's see the math example. Okay, so for the floor system of column system is given the response spectra damping ratio files with the ground motion data is from the Kobe. Earthquake is jet value is found 0.55 and L centro is 0.31, and calculate the elastic peak deformation and base shear for the column this column. And we know that 20 into 5 is the floor system. The floor is dimension is 20 feet by 10 feet, and weight is given to 50 psf including all load. All load mean dead load, live load, and partition and random all. And supported by 50-inch diameter of column and 20-inch non-meter of column, and each column 10-meter height, and use K equal to 12 pi by L. And no, we are using W, as we know that 10 into 20 into 10 is a floor system is given here 10 to 12, and 250 is given the PSF including one load, dead load plus live load. M equal to found W into G, which is divided by 32.5, and found yes. And E is given here moment of inertia we calculated, and K equal to 12 pi by L using this equation, and Kb equal to same, and adding 2 K, and in this way we found the natural frequency 23.69, and time period equal to 0.26. And we will not calculating C value here to C equal to 25 root over km. This is not for structural response. This is another C, so this is dumping C. So we will taking C from the Kobe or earthquake or L center ground motion, as we are seeing from this type of ground motion form. We are taking C value with respect to of T. When T will found 0.26, then we will calculate C 1.98 from Kobe. And the same way we found the L center ground motion. When we will found that time period is 0.26, then we will found the C below C structural response is 2. Now we will calculate the base shear for Kobe. We are putting all these below and just changing the C below 1.98, and found 54.7. For L center we will found C equal to 2 we below, and putting all these below, and L center equal to 31.3. And the deformation equal to P equal to KU. So we are putting the value of P value. This base shear we are calculating using this P. So P is nothing but P is the base shear, and found which is elastic deformation 0.57 for elastic peak deformation. And the base shear for column 1 we can see 38, and column B in found 15.93. And 2, if we calculate it in 2, then it will be 54.7. So these are the we can see here. Another example you can see in here, the figure is shown below. The superstructure and substructure of bridge span is 6 arch spire, each of the 20 feet of the 10-meter diameter, and structural mass is consist of the 100 feet long RC pier. Average section is 15 into 6, and 5 meter long was bridge pier, and deck and whiting 2 feet cube per feet. So these are the mainly Padma, or what I'll say, Padma bridge. Now we have to these are the practically taken from Padma bridge. Now we have to calculate the time period, elastic base shear, and elastic deformation of each pylon using new BNBC means BNBC 2020 for June 2, and soil type, and for soil type SB, and dumping ratio is 5%. Now we're calculating 5. We've been taken 5, and 50 feet is taken given in question 500 feet. 500 feet is long bridge is given, and 20 cube feet is given the weight, and and we have been found W. And how we'll get the m equal to W by G, and found E equal to given, and moment of inertia is found, and pile for pile 12 pi by L. We have been using six pile in Padma Bridge. We have been taking all the given in question, but we have been using we have used 6 pile. That's why you will multiply with 6 and found this value, and now we'll calculate the natural frequency W, and found 2.35, and time period is 2.6. Now this is not structural response, this is the damping ratio, that's why we will not use C. Now given the soil sites SB, then we will S equal to 1.25 and S TB equal to 1.5 and TC equal to 5 and TD equal to is given. So if we know that TD is greater than 0.35, then we will use this formula as 3 or 4 formula is given in question. Sorry, it will be given on the here. So if we find the value of T is which is 5.36, which is greater than TD, then we will use the here. So TD greater than TN. So this formula will be used. So TC into TD, TD square TC into TD. Yes, this formula we have used as the condition of this condition, and found C value is 0.425 and Z value is given here. This is the equivalent static method we have been used, and putting all this value and found the base share 6 to 4 kip. For base share of each pile, we have been taking the 6 pile, then we divided by 6 and found 104. The deformation of each pile equal to P equal to KU, and found 3.96. So elastic deformation of each pile we can say 3.96. Now we can see another example, which is 12 feet long vertical cantilever pipe is given E equal to and supported 5 kip or support to the kip, and determine the maximum deformation and bending stress cantilever due to BNBC new BNBC 2020 equation, and response spectrum for Z is Z value for Dhaka Z value is 0.2 and dumping ratio 2%, and soil is SB, and with pipe dimension is given, all the dimension is given. W equal to is given 5 kip, is 5 kg is given, and we are calculating M is divided by G, and E equal to found, and E equal to and I equal to pi as this is the circular, then that's why moment of inertia has been found this way, and K equal to 3A by L as the circular and hollow, and omega equal to root over km we will use this here, and timing 1.52 will use, and we will not this use. This is not structural response, this is just damping, it is related to damping. So if we calculate the damping C, then we have been found the soil category 1 2 as 1 2, and TB equal to 0.5 and TQ equal to 0.5, then TD. So we have been seen the TD TN we have been found calculated 1.52. So 1.52 is between C and D. So if we go the between C and D, then we will use this formula. Then we can use this formula. So we have to use this formula. Why? Because of the condition of this. That's why we will be using this formula. And then damping ratio 2, and we will getting the value of eta is 1.19, which is greater than 0.55, and in this way we will using on the eta value is 1.9 here, and found C value 1.18. Now we will using C value here 230 into Z by C, and we will using I into R, because the elastic base shear, when we will see the elastic base shear, then we will use neglect I by R, because we are seeing the plastic deformation is going here, and as we are, if we use R, then elastic deformation will not consider, the plastic deformation will be here, and found base shear 0.95, and we will calculate the deformation K equal to F equal to K, which is found deformation 0.35. I will get the F value. F value is nothing but it is the base shear or elastic base shear, and moment if you calculate the moment Force into perpendicular distance force is nothing but 0.59, and distance is L. L is given the we have been seen the length, and found 9.45, and now we calculate the stress My by I, and found this value, and D and Di, D out and D in our value is given, T is thickness is given, is all the dimension given. Then we found W, and we'll calculate moment M, which is mass, and moment of inertia, and K value, and omega equal to 0.89, and time period will be 0.114. As per soil report, the SB S equal to 1.25, and TB equal to 0.50, and T 0.5, and TD equal to 2. Now we've been found Tn equal to 1.13, and is between TC and TD, and found C value 2.29. So we can see when the stiffness is increased, then the natural frequency will be increased, but time period will be decreased, but C value with the damping structural response C will be also increased. The base shear will be found the C value 2.19, and putting all these value, and base shear equal to 1.6. So it will be increased as previous, as we have been found base shear 1.79, and it will be increased here. And the deformation also we have been found 1.63, and moment we have been found 241, and the bending stress 22.9, which is decreased, as we have been found 9.46, but here we have been found 22.9. So we have been seen when you increase the section, then it is decrease the bending stress. But base shear is when is increase the section, then bending stress decrease, but the base shear is increased. So base shear is not a solution for. The section increase is not solution for increasing in terms of bending stress. How we'll get this? If at first we have been taking D value here, we have been seen here. We can see here D value, another D value. But if we change the D value, then we have been found the different parameter. So let's see another example. The figure given below show the change form of 20 meter height of the tree, winter and spring. Average diameter of the tree trunk is 15 inches, and while the weight is assumed constant at top is 100 pound in winter, and 100 pound is winter, and 200 is pound spring. Calculate the natural frequency in tree, winter and spring. Use BNBC, it will be 2020, and calculate the elastic base shear and working in tree, winter, spring. Assume the modulus of elasticity 2000 KSI, and that is in Dhaka and soil type SA, and W equal to given 100 pound, which is 1, and M equal to W divided by G, and WS is given 200, and MS. W means winter, S means spring, and we have been using spring. And ES given 200, and a modulus of elasticity for moment of inertia for spring and winter are same, and we have been used the K stiffness value, and modulus of natural frequency is 14.79, and time period 0.15 for winter. For spring, natural frequency 28.87, and spring 2.22. And now we're calculating elastic base shear for winter. We've been damping ratio 5%, and we're taking CT and Z value, and found T equal to C value on 2.5. For spring, we have been found C value also 2.5. So elastic base shear we have been seeing. We have been taking all values. C in W value is change, which is taken 1, and the W value is spring is 2, that's why we've been seeing the base shear is 0.33 and base shear is 0.66. So this lecture is ended. I'm creating another value for how to make a response spectrum. So if you I'm giving the another link for calculating response spectrum. Okay, so if you have any question, then let me know. Thank you everyone. I hope you can understand here a little bit, and you can also mm, learn something response spectrum and equivalent static force methods, or you can say this is the design spectrum. Oh, okay, thank you everyone for your patience. If we have any question, then let me know. Thank you for your patience.